Okay, hello, this is the solutions for assignment 13. Question 1 here. Monochromatic light falling on two slits 0.018 millimeters apart produces the fifth order bright fringe at an 8.6 degree angle. What is the wavelength of the light used? So this is the fifth order bright fringe, and we have two slits, so I'm going to use my double slit interference formula for maxima, because this is a bright fringe. We are told that this is fifth order. That means m equals 5. And we're asked for wavelength. So rearranging this for wavelength gives us this formula here. Plugging in, we are told that the separation is 0.018 millimeters. So converting that to meters by multiplying by 10 to the power negative 3. We're told our angle is 8.6 degrees all over 5. And I got a wavelength of about 5.4 times 10 to the negative 7 meters. Okay, so that was question 1. Question 2. Monochromatic light falls on two very narrow slits, 0.048 millimeters apart. Successive fringes on a screen 6.5 meters away are 8.5 centimeters apart near the center of the pattern. Determine the wavelength and the frequency of the light. So again, we have a double slit interference question here. So I will use our formula that involves fringe spacing for double slit interference. And that is this one here. Now, these are successive fringes, so I will say that m equals 1. And we are asked for wavelength and frequency. So first I will solve this for wavelength. So I get yd equals L, because we're saying that, or yd over L equals lambda, because we're saying that m is equal to 1. Y is my 8.5 centimeters converted to meters. D is the split spacing of 0.048 times 10 to the negative 3 to convert millimeters to meters, and L is already in meters. That is 6.5. And computing all of this gives me a wavelength of 6.3 times 10 to the negative 7. I almost wrote 3 meters. So that is the wavelength of the light used. Now, to find the frequency, I will use our wave equation. However, this is the one specifically for light or electromagnetic waves, because I've replaced the v for velocity for wave speed with c, the speed of light. We are looking for a frequency, which is equal to c over lambda, which is equal to 3 times 10 to the 8 over 6.3 times 10 to the minus 7, which gives us a final frequency of 4.8 times 10 to the 14 hertz. So that was question 2. Question 3. Light of wavelength 680 nanometers falls on two slits and produces an interference pattern in which the third order bright red fringe is 38 millimeters from the central fringe on a screen 2.8 meters away. What is the separation of the two slits? So again, I'm going to go ahead and use this formula for double slit interference again with fringe spacing. And we are told that this is a third order. So m equals 3. And we are looking for the separation, so we'll rearrange this for d. And plugging in our values, we get 3 times 680 nanometers times our L, which was 2.8, times this spacing, which was 38 times 10 to the negative 3 for millimeters. And plugging all of this into the calculator gave me 1.5 times 10 to the negative 4 meters. So that was the first page, questions 1, 2, and 3. Question 4. A parallel beam of light from a helium neon laser with a wavelength of 633 nanometers falls on 2 very narrow slits, 0.068 millimeters apart. How far apart are the fringes in the center of the pattern on a screen 3.3 meters away? So, using our same double slit fringe spacing formula here, we are looking at the fringes in the center. So we're going to say that m equals 1. And we are looking for the fringe spacing. So that is y, no need to rearrange. So we can just go ahead and plug in right away. 633 times 10 to the negative 9 times 3.3 for L, all over 0.068 times 10 to the negative 3. And this leaves us with about 3.1 centimeters as our final answer, or 0.031 meters. I wrote that my answer in centimeters here because so far I've been giving you y fringe spacing in centimeters. 5. 2 narrow slits separated by 1 millimeter are illuminated by 544 nanometer light. Find the distance between adjacent bright fringes on a screen 4 meters from the slits. These are adjacent fringes, so m is going to be equal to 1. And again, this is double slit interference involving fringe spacing. So I use the required formula. We are looking for the distance between adjacent bright fringes. So we're looking for y. We are given 544 nanometer light. We are told it is 4 meters from the screen, and we're told the spacing is 1 millimeter. This is 1 times 10 to the negative 3. I've just written times 10, or 10 to the negative 3. No need to write times 1. All of this gives me an answer of 2.2 times 10 to the negative 3 meters. A little bit smaller, so I didn't bother writing this one in centimeters. For question 6, by what percent is the speed of blue light of wavelength 450 nanometers less than the speed of red light of wavelength 680 nanometers when traveling through silicate flint glass? The index of refraction is 1.4831 and 1.4754 for blue and red light respectively. So I'm going to have to find the speeds using this equation. The velocity of the speed of light in a medium is equal to the speed of light in a vacuum divided by the index of refraction for that wavelength in that medium. First, let's find the red speed of light. Plugging in our numbers here. I end up getting something I forgot to write down. I have the final answer written down, but not the in-between working out numbers. That's my red speed. My blue speed, using the same method, equals this here. These are both in meters per second, but they aren't my final answer, so I'm not going to bother writing down the units right now. So, percent difference formula. I end up getting a final answer here of 0.52% slower. Now, I didn't bother writing out the full equation like I normally do with the huge numbers. I didn't want to because the numbers are huge. Instead, I color-coded red and blue, so I hope that makes it clear what questions are where. So that was the answer for number 6, and, well, I guess 4 and 5 on page 2 of this assignment. Question 7. A light beam strikes a piece of glass at a 65-degree incident angle. The beam contains 2 wavelengths of 450 nanometers and 700 nanometers, for which the index of refraction of glass is the same 2 indexes as before, respectively. What is the angle between the 2 refracted beams? So this here is very, very similar wavelengths to question 6, so I just ended up using the same indexes of refraction. And if you've looked ahead at question 8, again, the same 2 indexes of refraction are used for similar wavelengths. Okay, question 7. This one here, we're going to have to do Snell's law twice to figure out what the 2 refracted angles are for each wavelength. So we're going to have to do it for red and for blue, and then find the difference of these 2 angles here. And they both have the same incident angle. Let's assume that N1 equals 1 for air. Let's assume this. So, setting up Snell's law, we get N1 sine theta 1 equals N2 sine theta 2. Rearranging for theta 2 gives me the arc sine of sine theta 1 over N2 which is equal to, well, actually not equal to, I gotta plug in numbers first. 65 degrees over N2 for red, that is 1.4754. Now, let's punch this in a calculator and see what it's equal to. Here I'm getting 37.8995769. And for blue, we end up doing the same. Same method as red. The only real difference is that my index of refraction changes to 1.4831, and this gives me an angle of 37.66836.901. And then what I'm actually looking for is going to be the red theta 2 minus the blue theta 2. And that's going to give me about 0.23 degrees. Again, I'm sure you can see with the color coding which angle goes where in that formula. I just don't want to bother out writing every single decimal. I'll write out most, though. So that was question 7. Question 8. This was, I believe, the biggest one on this assignment. A parallel beam of light containing two wavelengths of 455 nanometer and 642 nanometer light enters the silicate flint glass of an equilateral prism shown here on the right, for which the index of refraction of the glass is 1.4831 and 1.4754 respectively. So again, the same indexes of refraction. At what angles does each beam leave the prism? Now I'm going to rename these phi 2 and phi 2. You'll see why. And I'm keeping those black and not color coding those as to keep a little mystery. Which one's which? You should already know. Okay, so what are we going to have to do to find these two angles here? Well, let's just look at one of the waves first. Let's look at this bottom one. What are we going to have to do to find this angle? Well, we're going to need Snell's law, and for that we're going to need this other smaller angle on the inside in here. And for that angle, we're going to need to know this angle here. And for this angle in here, well, we're going to need Snell's law and the given angle of incidence. So we're going to have to do Snell's law, figure out what this angle of incidence is over here, based off of this angle of refraction, all to find here. So for each ray, we're going to have to do Snell's law twice, plus a little bit of geometry to find this incident angle. So let's go ahead and start with red. Again, let's say that N1 equals air, which equals 1. So I get my first Snell's law set up. And again, N1 is 1, so we can ignore it. Rewriting for theta 2, this is the arc sine of the sine of theta 1 over N2. Plugging in my numbers. This is the sine of 45 over 1.4754. And punching this in my calculator gives me something a little bit over 28. Gives me this number here. Now, for the little bit of geometry, this is my angle of refraction of the red ray. So this is my angle as measured to the normal here. I need my angles of incidence here and here. And so from class, we have our formula of theta 2 plus phi 1 equals A, where the angle A is the apex up here, so that is my 60 degrees. And I am calling all of the angles on this left side, this first air prism interface, theta. I'm using theta to describe all the angles on the left. I'm using phi to describe all the angles on the right. So therefore, phi 1 is what I will be using to represent my angles of incidence at the second interface when the light is leaving the prism here. So what I am looking for here is phi 1, that equals A minus theta 2, which is 60 minus the number we just got, which gives me 31.362662638. Great, so that is my angle of incidence. Now, and I'll break these up with dashed lines, just so it's a little bit clearer. My second index, or Snell's law here, this is going to be N2, because we are starting in the prism. Sine of phi 1 is equal to N1, because we're leaving and going to air, the original medium again. A sine phi 2. I'm looking for phi 2. So that is just equal to the arc sine of N2 sine phi 1, which, plugging in numbers, gives me 1.4754 times the sine of that 31.362662638 degree number. And that gives me something I must punch into my calculator. I got 50.16 degrees. And that was the angle the red beam left the prism at. So, for blue, this is the same method, just with different indexes of refraction. So for blue theta 2, this is the arc sine of the sine of 45 divided by 1.4831. So theta 2 is equal to 28.47506132 degrees. And again, this here is the same formula, same method. So phi 1 equals 60 degrees minus the number we just got, 475063132. So phi 1 is equal to 31.52493.868. And setting up my final sine law here. Again, same method. So I use the arc sine. I use my index of refraction for blue. And I take the sine of 31.52493.868 And I get a final answer of 50.85 degrees. So we see that the blue light, the angle here is ever so slightly larger at both cases here, in both situations. 31.5 versus 31.4 rounded up. So we know that the blue light will have a slightly larger angle here. Okay, so, oh wait, that was the angle of incidence I was looking at. That's why I was a little confused. The angle of refraction of the red is 28.6 versus 28.5, so yes, the red should be on top. So, going back, this is not phi 2 black. This is phi 2 blue. This is phi 2 red. That makes more sense to me. My little rule of thumb I always use to remember is that longer wavelengths bend less. They have less bends in them. I imagine it as having a lower frequency, so there's less ups and downs, less bends, so they bend less when they refract. It's kind of how I remember it as a little rule of thumb, which is why I figured out I was looking at the wrong angle quickly there. So that makes more sense. The red light is the one on top. The blue light is the one that bent more. So those were the answers for question 7 and 8 on page 3. Question 4. Page 4. Question 9. If 680 nanometer light falls on a slit 0.0425 millimeters wide, what is the angular width of the central diffraction peak? We're looking at a single slit here. So we are going to look at single slit diffraction, and we're going to look at the minima, because the central diffraction peak will be bright. The first ring around it will be dark. That will be a minima. So here I have sine theta equals m lambda over d. We are looking at the first set of minima, so n equals 1. That leaves me with theta equals the arc sine of lambda over d. Plugging in some numbers here, I have a wavelength of 680 times 10 to the 9 meters and a slit width of 0.0425 times 10 to the negative 3 meters. And that will give me about 0.9 degrees. However, we are not done. This is only half of the angular width of the central diffraction peak. So what we have done is, if this is my peak, we have calculated this angle theta here, where we want this angle here of 2 theta. So multiply everything by 2, and we get our final answer of 2 theta equals 1.8 degrees. That is the angular width of the central diffraction peak. This question being worth 1 more point than other ones similar to it, so this is worth 3 points, should have hopefully given you a little bit of a clue that there is one extra small thing to do after the initial calculation. So hopefully that reminded at least somebody. Okay, question 10. When blue light of wavelength 440 nanometer falls on a single slit, the first dark bands on either side of the center are separated by 51 degrees. Determine the width of the slit. So again, single slit diffraction. And so this is the first dark bands. So M equals 1. And we're asked for the width of the slit. So I'm going to rearrange this and substitute M equals 1 in. This here is now my formula. Plugging in numbers. I have my wavelength up there. And this is the sine of 51 divided by 2. These are the first dark bands on either side of the center. So these dark bands are here and here. So what I have given you is this full angle, 51 degrees. So we need to divide that by 2 for this one. Once you have your numbers plugged in, ready to go, we get an answer of about 1 times 10 to the negative 6 meters, or just 10 to the negative 6 meters. Both of these are fine. So that was question 10. If you had gotten the multiply by 2 part of number 9, you would have also gotten it here. However, if you messed that up on number 9, you would have also messed it up on number 10, which is why 10 was only worth 2 points. I didn't want to end up taking away 2 points for the same single mistake. That was questions 9 and 10 on page 4. Last page here, 5. Questions 11 and 12. So question 11. How wide is the central diffraction peak on a screen 2.3 meters behind a 0.0348 millimeter wide slit illuminated by 558 nanometer light? So this is not angular width. This is something else entirely, but we still need to find theta anyway. So again, we're looking at the central diffraction peak. So in our formula here, M is going to be equal to 1, and we are looking for theta. So this is the arcsine of lambda over d again. Plugging in some numbers, we get 558 times 10 to the negative 9 over 0.0348 times 10 to the negative 3. That gives us a theta of 0.918747556. And for the width, we get 2L tan theta is our formula. And plugging in 2 times 2.3 times the tangent of 0.918747556, we get a width of 7.38 times 10 to the negative 2 meters. And that was question 11. Last one here, number 12. Monochromatic light of wavelength 633 nanometers falls on a slit. If the angle between the first 2 bright fringes on either side of the central maximum is 32 degrees, estimate the slit width. So we are looking for D here. And sine theta equals m lambda over d. Rearranging for d, that is m lambda over sine theta. Now, when we go to plug in, there are some things to notice. We are looking at the first 2 bright fringes. So our m must then be equal to 3 over 2, and the angle is either side of the central maximum, 32 degrees. So for the same reasons as before, theta is 32 degrees divided by 2, so 16 degrees when I go to plug in. So plugging in all my numbers, I get 3 over 2 for my m. My wavelength is 633 times 10 to the negative 9 meters over the sine of 16 degrees. This gives me a slit width, capital D, of 3.4 times 10 to the negative 6 meters. So that is my answer for question 12 here. That was everything for assignment 13. If you have any questions, please email me or ask me in class. Thank you.